Hey everybody. So today's lesson, I'm about to put up the next two, I think. Both have to do with our next topic, which is chapter 9 stuff. And this stuff all has to do with collisions. Basically, what happens when things come together, how is momentum transferred, how is energy transferred. And then we'll get into the next section, the last part, which has to do with doing work when we actually have things that come together. So it's kind of combinations of a couple of different chapters. So you just kind of have to hang in there with me since we only have a real limited amount of time left. So like I said, this one is about collisions and about what happens when you start to apply forces to objects and when two different things come into contact with one another. So first part, in terms of dealing with this one, it's really important to understand the big concept in here is the concept that basically not all collisions are the same. I know that's kind of what it says on here. So here I've got an example of dudes jumping off of roofs. Basically, right? And one of the things to know is that when you drop something off of a 10-story roof, or a 10-story, one-story roof, about 10 meters or so, is that not each collision with the ground is the same. There, in some of these stories are these little videos that's on here, just entertainment, and then some of these there's probably injury to follow. It's not really about the height that you're falling from. It's about what happens when you get to the end of that particular journey. And the joke is, I think I have it on the next slide, it's not the fall that kills you, it's the sudden deceleration at the end that counts. Remember that force equals mass times acceleration. And with all of these, you're talking about a similar sized mass that's coming into contact with the ground, relatively coming from the same height. So you should have basically the same, approximate final velocity at that instant right before you hit the ground. But what's different in all of these is the rate at which the deceleration will happen. So this gentleman up here at the top left, he's more or less jumping onto concrete. His rate of deceleration is going to be quite rapid. So he's going to go from whatever his VF is to zero in a very short distance. Smack, you're going to be done. If you're talking about the same gentleman here that's about to jump on top of this garbage can, assuming that he hits the garbage can, he'll have a little bit of a crush zone before he dies, which is why these things tend to make it onto fail videos. Our other friends, the two Chads over here jumping into the pool, or these two knuckleheads jumping onto their trampoline, again, their rate of deceleration is quite a bit different because they've got something different that they can land on. Same thing with our friend up here in the snow. When you're landing on a softer surface, that amount of time in which that you're doing your deceleration is actually quite a bit different. This is actually a key thing towards how we can do all kinds of crazy decelerations as long as we do it over a long period of time, or conversely, over a relatively long distance. So, for example, our friends that are jumping here into the water, if y'all have belly flopped into water before, you know that jumping flat onto the surface of water is not a pleasant experience. It feels more or less like you're jumping onto something that's firm, so to speak. If you then dive into it and you push that water apart, then you can kind of change the rate at which you're hitting that water. So again, you're either playing with the concept of how much distance are you accelerating in or how much time are you accelerating in, and all of these are about how we can modify collisions to make them a little bit less difficult. The key concept here, and this is the actual physics term, is this physics term up here, which is something called impulse, and this is an actual vocab word. Impulse has to do with the rate at which you're applying a force to an object, just not how much force is being applied, but then something about the time over which you're applying that force. So again, are you literally just doing a quick slap, or are you giving it something a push? Those make a difference in terms of how you are transferring energy basically from one object to another. And again, the key concept here is something called impulse. It's not just the force that's being applied, but the time has to be involved in there, the rate that's involved with that. So when we're trying to do impulse problems, impulse is defined mechanically as force times times. It's literally F times T is what we call impulse. And impulse is a pretty straightforward straightforward concept. You guys have seen something like this before when you think about even like a rocket that's launching. Is it being just a single quick push, or is it being pushed up over a period of time? And we would kind of call that, a lot of times people call that thrust, although thrust has a slightly different meaning to it. Similarly, if you think about a football tackle that's being that's happening between two massive individuals, impulse is the rate that they are applying that force one another. So think about two guys coming in to collide with one another, and they sort of grab one another and sort of continue together, versus those kind of like bam kind of collisions where all of that force is being transferred from one person to the other in basically just a quick instant. That's that concept of impulse. So you can either apply it over a long period of time, which really increases your amount of impulse, or a real quick, short amount of time, which would decrease your impulse, just a quick little slap, as opposed to a true something with duration to it. And anyway, it's something that continues through time. So I put a couple little equations on here. Obviously, F equals ma. That's Newton's second law. Force equals mass times acceleration. In the second equation here, what I'm rewriting is equation for acceleration, basically as the change in velocity over time. And then the third equation down here is kind of the key one as we get into this physics part, where I've literally just multiplied both sides by time. So I've kind of moved the time up from here so that it's on the other side. So I've got F delta T equals M times delta V. These things are important that we've got in here. So this thing right here is what we call impulse, F delta T. Force times time is what we call impulse. This thing over here, mass times its change in velocity, is something that we call momentum. So we actually have two different big ideas here that are kind of related to one another. That when we have an object and change its velocity, I must have applied a force to it, and then there must have been some time that's involved with it. So if I have a bigger change in velocity, I either have a bigger force, or I was applying that force for more time. Obvious. I mean, once you start to think about kind of how these relate together, it makes sense. But the algebra to kind of get to this point isn't always obvious to students. So again, F delta T, I'm writing on my screen. F delta T here is known as impulse, and M times delta V, mass times change in velocity, is something that we call momentum. And I know you've heard the term momentum before in terms of what it is. Whoops, lost it. Get for randomly poking things on my screen. Come on here. Let's go to the next screen. There we go. So how do we apply these in a way that makes sense? Come back here. So this particular thing is called the impulse momentum theorem. And this is the important mathematical piece that you need to use to be able to kind of address these. So I didn't pick the letter on this. I apologize. But the letter that we use to abbreviate momentum is P. It's a lowercase letter P, not even an uppercase letter P. Again, I know it's a little bit weird. I think the M's were already taken by other things. So they just use delta P for this. So here's what the impulse momentum theorem is. Impulse is F delta T. And F delta T, impulse, results in a change in something's momentum. Momentum is basically defined as M times V, how much mass something has and how much velocity something has. It's a lot like a force, which is mass times acceleration. So P equals M times V, again, which is really similar to force equals M times A, which should be a capital F. Very similar. Something's got mass, and then something is moving. So what this is a little bit different here is it means that an object can have momentum if it's going at constant velocity. Again, it doesn't have to be accelerating. In order for something to have force, or to be able to apply a force, has to be accelerating. But momentum is when an object is simply moving. So in other words, if an object is changing its motion, delta V, that means we're going to have a delta momentum, a change in momentum to it. So again, this thing is called the impulse momentum theorem. Momentum is mass times velocity. A change in momentum is the result of impulse, which is F delta T, and it's also written as M delta V, mass times the change in velocity. Over here on the right, I just have a couple of different ways that delta V can be represented mathematically. So you can either do MVF minus MVI, final velocity minus initial velocity, or because momentum or mass isn't changing, you can just do whatever the change in velocity is. One of the little tricky things to kind of keep in mind here is that there is a difference between momentum and impulse. Momentum is mass times velocity. That's all momentum is. Something that has mass and it's moving. impulse is related to its change in momentum. And that's a real different thing. So it's a real subtle piece, but momentum is literally mass times velocity. Delta P is what we would call impulse. It's change in momentum. In order for having something change its momentum, that means there must have been a force applied somewhere. And again, how do I know there was a force? If it's changing its velocity, there had to have been acceleration somewhere. Therefore, there would have to be a force that's involved to it. So P is momentum, triangle P or delta P is impulse. So here's a couple of examples of how we would apply these. Again, these are just math problems in terms of making these things work or kind of applying them on there. Probably for you, many people can hit pause at this point and kind of practice these out. But these are examples of how we would use the impulse momentum theorem to solve some math. So here we've got a bowling ball. We're applying a force to it for a certain amount of time. We've got, again, 168 newtons of force. We've got 7.3 kilogram bowling ball, and we have 0.4 seconds to it. It's important to know that in this particular chapter, kilograms, because we're dealing with force, kilograms are considered to be the standard unit, not grams. And that's because our units of newtons are always related to kilograms as well. So that's why this is, we don't have to do any weird conversions in here. So with this, what's the bowling ball's change in momentum? All right. Well, we can kind of figure out it a couple of different ways. Delta P equals F delta T, which equals to M delta V. So something along those lines, depending on which pieces that we have. So this is for A. Which ones do we have? Well, if I want to know its change in momentum, that's triangle P. I have a force and I have a time. So my force is 168 newtons. My time is, 0.40 seconds. So 168 times 0.04, just 0.4, is known as Math Geniuses 67.2. Units for this is kind of awkward. It's a Newton second, NS. That's pretty much it. It's not very exciting. It's also, we'll get to some other units that we get for this in a little bit, but a Newton second is close enough towards what it is. Change in momentum is a Newton second. Bizarre, right? What is the bowling ball's change in velocity? Would be question number 2. Well, delta P equals M delta V. So with this one, I can use my answer here. Delta P is 67.2. Again, this is Newton seconds. I can figure out what my change in velocity is here by talking about my mass of my bowling ball, 7.3 kilograms. And then I know that delta V is after this. So again, math, 67.2 divided by 7.3. And in this case, our delta V is a change in velocity of 9.21, meters per second would be our change in velocity to this. In this case, it's considered to be positive because I'm applying a force to it, so I'm probably accelerating it, speeding it up. I guess looking at my problem, I should only have 2 sig figs. This one should be 67 Newton seconds, and this one should be 9.2 meters per second, so with 2 sig figs. There you go. So again, with these, the math on these is not very difficult at all. If you can remember what your impulse momentum theorem is, that you've got the change in momentum is F delta T, impulse, which is also equal to the change in momentum of it, which is M delta V. All of those are sort of equivalent concepts. Last one, good chance for you to take a pause on this one and see if you can apply impulse momentum theorem here to a baseball problem. Again, take a moment, hit pause, and see if you can kind of work through these. Again, these are going to be using our equation. Change in momentum is F delta T equals M delta, V. Sorry, my triangle there got a little bit funky. And see if you can kind of apply those to this particular problem. All right, hit pause, give it a shot, see if you can work it out, and I'll be right back. I think this is our last slide for this. Okay, welcome back. I'm assuming that you left and hit pause and tried these out. So what's the change in momentum of the ball? Again, change in momentum is delta P. What are some of the pieces of information that we have? Well, we can use F delta T. We can use M delta V. Any of these will work. In this particular case, I've got a couple of different velocities to it. So I'm going to use the M delta V to answer this particular problem. delta P, sorry, equals M delta V. Our mass of our baseball is 0.145 kilograms. Again, kilograms is the standard unit of mass in these problems, so we don't have to try to do anything else funky with it. And then we've got delta V. In this case, it starts at 42, and then it gets increased back at 58 meters per second. So 58 meters per second. And then our other one is 42. So meters per second. We've got a little bit of a problem here, so I'm gonna point this out in here. Here's VF, and then here's VI. Our initial velocity was 42, and our final velocity was 58. So if you did the problem this way, you're actually pretty close. Our change in velocity, 58 minus 42, VF minus VI, would be a delta V equals 16 meters per second. So 16 times 0.145 gives me a change in momentum of 2.32. And again, in terms of this, it's actually Newton seconds would be our impulse for this. It's kind of weird. Kilogram meters per second is the final unit for this, or Newton seconds. So we have a problem with this, though. Our delta V here is actually not 16. Really common mistake for students to make, so don't worry about that. But let's talk about why that is. So a baseball is being pitched at 42 meters per second. Okay, bam, 42 meters per second. And then it's being hit horizontally to the pitcher at 58 meters per second. This is 58 meters per second. And as soon as I draw this, you can kind of see that they're not really quite the same. Depending on how you want to do signs for this, these are going to be at opposite directions. So one of these has got to be negative and one of these has got to be positive. And it really doesn't matter which one you do. If we call this one positive, then this one's negative. And if you look at your delta V here, it's got to be VF minus VI, which is actually negative 58 minus 42. It's a much bigger change in velocity than most students recognize. So 58 and 42, our actual change is negative 100 meters per second. Again, why is it so big? Because it's actually changing direction. It went in at 42 and it came out at 58. This is a really common mistake. So with this one, again, this is not quite the right answer, although it's pretty darn close. It shows that you kind of understand something about it, but this is definitely a 1-point problem. Our 2-point, this would be a 1-point mistake on a 2-point problem. So really what you should be using here is 0.145, and then our delta V is actually negative 100 meters per second. This is the way that this should be done. Again, if you did it this way, don't feel bad. I do this problem as a way to kind of point out one of the things that's a common mistake that students make. So 0.145 times 100. Our impulse here, our change in momentum, is actually 14.5 is the actual value. And it would be negative. Why would it be negative? Because it's changing direction. So its initial impulse, its initial momentum was this direction, and its final momentum is going the other way as it's leaving the baseball bat. So again, a little bit of an awkward kind of a problem, but that's really what it should be in terms of being able to do that. All right, part B. Again, if the ball and the bat are in contact for this many seconds, what's the force being applied? Again, this is going to be using, F delta T equals delta P. So once you've figured out what your change in momentum is, you can kind of plug those values in. So force would be this times 4.6 times 10 to the negative fourth. Real small number, because usually when you're hitting something with a baseball bat, you're really not in contact for that long. And then your delta P is negative 14.5. Again, I'm going to use my correct value. If you use the other one, you can kind of figure out what this would be. Force would be equal to 14.5 divided by 4.6 times 10 to the negative fourth, which gives a really, really big value, 31521, by the time we do our math on there, which is going to be 2 sig figs, 3.2 times 10 to the 1, 2, 3, fourth, and then force is going to be in newtons. If you gave this a negative sign, that would be correct. because again, you're pushing it. That's just a directional as opposed to pulling it the same way. It's coming in this way, and you're applying a force to make it go the other direction. So your force is opposite to the direction of its original motion. That would give it a negative sign. So there you go. How to apply the impulse momentum type problems to it. A couple key things is to make sure that you've got your equation down there. Change in momentum is F delta T, also known as impulse, and it's M times delta V. And then this problem highlights one of the key mistakes that students make is to make sure that you're checking your velocities to make sure that your velocities, if they're changing direction, that your delta V's can actually be quite large. And as a result, your forces can actually be quite large as a result of that. So there you go. A basic introduction to the impulse momentum theorem and how you do some of the math problems with that.